Lecture 22 covers sections 7.2 through 7.4. At the end of today's lecture, you should be able to analyze the behavior of a capacitor as a function of time and construct an expression for the behavior of capacitors that are connected in series and parallel configurations. For us to begin, we have to talk about energy storage elements. Inductors and capacitors are dynamic devices. That is, they have a time dependence of behavior. And this requires us to either use an integral or differential formulation to describe their behavior as a function of time. These devices differ in contrast to linear devices, such as resistor, which are static and modeled using linear algebraic equations. These differential equations that we use to describe the behavior of these dynamic devices gives us a time history of the accumulation and or discharge of energy from the device. That is, capacitors and inductors can store or dissipate energy as a function of time. A capacitor is schematically shown on the left and represented physically on the right. On our left-hand side image, we have current flowing into a capacitor, I, as a function of time, where a voltage potential exists across our two plates. A capacitor is denoted by two parallel plates that are not connected. In real life, our capacitor has two parallel plates that are separated by some distance. Now, energy is stored within an electrostatic field that's generated between these two parallel plates. Capacitance, a measure of the energy stored, is expressed as epsilon A per D, where epsilon is our dielectric strength, A is the area of our capacitor plate, and D is the distance between the two. Our capacitor has units of farads. A farad is an amp second per volt. Now, what's cool about capacitors is you can increase the area between the two plates to accumulate more charge. Or if you decrease the distance between the two plates, you also increase the charge. However, epsilon, your dielectric constant, has to be strong enough such that charge will not jump from one plate to the other. Now, these three parameters are all based upon physical values. Epsilon, the dielectric constant, can be that of air if there's nothing between the two plates, or that of insulation if you place an insulating material between the two plates. Now, the constitutive equations describing the behavior of a capacitor is as follows. The charge stored as a function of time is equal to our capacitance times the voltage potential established across our capacitor, i.e. Q is equal to CV. Now, if we recall our expression for current, our current is the time rate of change of charge. Therefore, we can say our current is equal to our capacitance times the time rate of change of our voltage, since our capacitance C is based upon physical parameters and does not vary with respect to time. Thus, we need a time-varying voltage potential for current to flow. If there is no change of voltage with respect to time, current will not flow through the capacitor. The voltage accumulated or discharged from the capacitor is equal to 1 per capacitance, the integral from negative infinity to t, i.e. our time of interest, of I of tau d tau. Or we can say this is our initial voltage potential across our capacitor, V sub naught of t, plus 1 over capacitance, integral from t naught to t, of I of tau d tau. Now our voltage potential must be continuous across this device since I of t is bounded.